These are the example questions we worked in class today. Let's work them out again so you can see how they're done. I want to find the pH of a 0.1 molar sodium hypochlorite solution. I can tell this is a salt because there's a cation and an anion. I can tell it's a basic salt because the cation comes from a strong base and the anion comes from a weak base. That means the sodium is going to be a spectator ion. I'm going to kind of ignore it, and we're going to write the equilibrium expression first with hypochlorite at equilibrium with, let's see, if we're going to call it a base, we got to remember to call it a hydrogen acceptor. So I'm going to make it accept a hydrogen and put it into its hydrogen hypochlorite form. It accepted a hydrogen from water, so what we'll be left with is hydroxide, ice. We can assume that since there is 0.1 molar sodium hypochlorite, it's 0.1 molar in hypochlorite. And I'll write down 0.1 molar hypochlorite. We'll assume 0, and 0 is the initial molarity. The change will be relative to x, and we'll assume that x is a small number, so at equilibrium, the molarity is the same. This involves equilibrium, so it involves a K value. But since this is a base reaction, we need a Kb. There is no Kb on the pink sheets for this, but there is a Ka for the acid form. Looking at the blue sheet with those values, I can see that that Ka is 2.9 times 10 to the negative 8. Ka times Kb equals Kw, so Kb equals Kw over Ka. 1.0 times 10 to the minus 14 is Kw, and 2.9 times 10 to the minus 8 is Ka. Grabbing my calculator, I can tell that that product is 3.4 times 10 to the minus 7. That's the Kb value. So that Kb is going to be products over reactants, or I can think of it as HClO OH minus 1 over ClO minus 1. So my Kb value, which we said was 3.4 times 10 to the minus 7, is going to be equal to x and x, here and here, that's x squared, over 0.1 molarity at equilibrium. I'm going to solve for x, and x is going to be both hydroxide and hypochlorous acid. So to do the math, I solve for x, and I get 1.8 times 10 to the minus 4. Now that value, as we said, is what we have for hydroxide and the acid, so I'm going to write that in here. 1.8 times 10 to the minus 4 and 1.8 times 10 to the minus 4. What I'm going to do with the hydroxide is convert hydroxide into POH. The POH isn't the final answer, but it's a good start to that. So I take this value, I take the log of that value, and I get 3.73 as my POH. Then I subtract that from 14, and that gives me a pH of 10.27. And that is my final answer. Notice that the answer is basic, and that's exactly what we expected from a basic salt. Let's try the other one now. In the second example we worked out today, we're finding the pH of ammonium chloride. I can tell that this is also a salt because we have anion-cation. So I can tell it's also an acidic salt because the anion chloride comes from a strong acid. It's essentially a spectator ion, and we're going to cancel that out. This is about ammonium reacting at equilibrium. And since we called it an acidic salt, we're going to call it NH4 plus 1, a hydrogen donor, because that's what acids are. So I'm going to make this donate a hydrogen, and when it donates a hydrogen, you're left with NH3. Ice. 0.25 molarity ammonium chloride means 0.25 molarity ammonia. 0 and 0. Losing X, gaining X. And assuming X is small, 0.25. We need a K value for this, but the kind of K we need is a Ka value, because this is an acid reaction. There's no Ka listed, though. So we recognize, again, when Ka times Kb is Kw, we can say that Ka equals Kw over Kb. 1 times 10 to the minus 14 over 1.8 times 10 to the minus 5. That Kb value is the Kb for ammonia. So when I find ammonia listed under the weak bases, I'll do this for it to get my Ka value. So back to my calculator. And I determine that the Ka is 5.6 times 10 to the minus 10. That's our Ka. And that is going to be equal to products over reactants. So that's hydrogen molarity times ammonia molarity over ammonium molarity. So with my Ka equal to 5.6 times 10 to the minus 10, I'll put that as products over reactants. Products being X and X, X squared, reactants being 0.025, or 0.25, sorry, and I'll solve for X now. And I determine X to be 1.2 times 10 to the minus 5. Now I'm going to write that in here for H and for NH3. But this is the one I care about, because this is hydrogen, and all I need to do is take the log of this number, and I have pH. So that's what we're going to do next. The log of 1.2 times 10 to the minus 5, and then taking that value and making it negative will equal the pH, and that gives me an answer of 4.93. That's my final answer, and that sounds reasonable because we expected this to be an acidic salt, and the pH is slightly acidic. All right, hope this helps. Keep working on that homework.